Welcome to part 5, the final part of the breeding value prediction module for the TLR course at the University of Pretoria. In part 5, we'll be looking at the inclusion of molecular information, so-called genomic information, in the prediction of breeding values for farm animals. We can get going. As I've said, this is in this part, we will be looking at the combining of molecular genetic information, that is the genomic information, with pedigree and phenotypic information for breeding value predictions. We've seen so far that the main sources to predict breeding values or the additive genetic value of animals would be the pedigree information, because that says a lot in terms of the relationships or the additive genetic relationships amongst animals, those additive genes that they share, as well as the phenotypic value or recording performance data in relation to contemporaries, where animals were subjected to exactly the same fixed effects or environmental effects. So there's another source of information that can be added to the prediction equations somehow, and that can be used then to increase the accuracy of prediction, especially in terms of sex-limited traits or traits that were not yet recorded or measured on a specific animal due to different reasons, the animal being too young, for example, or simply not being measured for a specific trait. So there are then specific reasons why this methodology has then been developed, and that can make a huge impact on the accuracy of prediction and obviously on a lot of other important aspects of animal breeding. And that then basically brings us to the key equation. I'm sure you all are familiar with the key equation. Um, the annual genetic change through selection. So you are selecting for specific traits, a group of traits, and your progress for that delta BV, or the change in the breeding values over time, equals the accuracy of your breeding value prediction or your genetic merit prediction, how accurate that you predict based on your models, your blood models or other models, the additive uh, value of a specific animal or the breeding value of a specific animal. So this accuracy or this correlation between the true breeding value and the predicted breeding value will determine how accurate you were in terms of ranking the animals according to their breeding values. That is the one factor. The next factor that is the intensity of selection or the proportion that you selected, and obviously this relies on a other factors such as the survival rate and the reproduction rate of in your population. So if you have a good reproduction rate and a good survival rate, so that's your fitness traits, you will have a bigger choice of selection amongst the animals available for um, replacement of the current population or the current breeding animals, and that will have a marked effect on your selection progress. Uh, the third element that will contribute to your progress or the rate of progress when selecting animals would be the variation in genetic merit. So this is basically the variation in the breeding values. Um, and obviously the accuracy of your prediction will also determine how much of this variation can you assume to be true variation versus not true variation. So basically that's above the line in the key equation, and you want these elements above the line to be as large as possible or the biggest variation possible. This is divided by the average breeding age um, or the average age of a breeding animal, or also called the generation interval, and you want the generation interval to be as short as possible. And we will see how the use of genomic information can have a marked effect on the generation interval in breeding stock, that you can actually select at a much younger age at the same accuracy or even a better accuracy of prediction of the specific breeding values. So the objective then is in your prediction to be extremely accurate at a young age and to rank the animals accordingly and to make a good choice out of the available breeding animals. Good. We have seen so far that the breeding value can also be determined or defined as for an animal as being getting half the additive genes from the sire and half the additive genes from the dam, but it's a random sample from each of the parents, and we would call that the Mendelian sampling. So basically, if this is known, if the accuracy of the prediction of the sire and the dam is very high, and you have a means of knowing what the Mendelian sampling is, you have a fairly accurate prediction of the breeding value of that animal that you consider as a selection candidate. So if you have a young animal and this young animal has not been recorded or measured for the specific traits, it's assumed that at that stage your prediction would be half the breeding value of the sire and half the breeding value of the dam. We also call that the parent average or a mid-parent value. So, and that is part of the problem in that your assumption is halfway between the parents and you do not take the possibility of a Mendelian sample into consideration. So if one had a means to predict this Mendelian sample earlier in life, your selection accuracy will be enhanced because of the higher accuracy of prediction. This figure illustrates the current state of affairs without the usage of genomic information for traits that are sex limited, such as, for example, in dairy cattle, where you cannot record some of the traits or the most important traits on the sire, and you want to make a decision on the choice of bulls for AI sires, artificial insemination sires, for example. So if this is a bull that's considered to be a possible candidate as an AI sire, you can select those bulls or those candidates when they may be young, fairly young, younger than a year old, but at this stage you only select them on parent average and nothing else. The first daughters of those bulls will only be born when the bulls are 2 years old, and obviously they must grow up, they must start lactation, even complete lactation, and only when those bulls are in the just about 5 years old, you can say that they are progeny tested. So you already have an extremely long generation interval before you have the first progeny test. And if this pattern repeats itself, it means that the sons of those bulls will only be progeny tested once these bulls are 10 years old. So a very long generation interval due to the fact that these traits are sex limited. They can only be measured on the females. To a large extent, if you want to select dams of sires, so cows that will breed AI bulls for you, you also have a fairly long generation interval. So you have the birth of the cows. She gives birth when she's about 2 years old. Her daughter's 4 years old, and the son will only be progeny tested once she's in the region of 7 years old. So if you think back of the key equation, this actually extends the generation interval tremendously, and the history has taught us in the past that it's an extremely long process until you are sure about the actual breeding value of an AI sire. So this is basically what happens in traditional breeding. We have seen we use pedigrees of animals and the records of animals, the actual weights or measurements on animals. We put that through a blood estimation, and we get breeding values on the other side. So this accuracy can only be increased if an animal has own phenotypic records, and we've just seen we have sex-limited traits, for example. It's impossible for a bull to have phenotypic records, and we increase the information of recordings on relatives, SIPs, half SIPs, full SIPs, and the progeny of those animals. So and that's the only way that one could increase the accuracy of the breeding value prediction for these animals. Okay, and then we can go over to the very first attempts in adding additional information in our breeding value predictions, and currently we will call that the so-called two-step methodology, and it's based on the fact that you have to build the so-called reference population, and a reference population is being built by getting the genotype information of some animals in the population. Uh, as I said, we call it a reference population, and initially the notion was that you needed at least 1,000 animals. Nowadays, the notion is that you need a few thousand animals, depending on the heritability of the specific trait that you want to use it for, where you basically use animals with an extremely high accuracy or reliability for their blood breeding values. You genotype those animals on a so-called high density SNP chip, so where a lot of the SNPs are known and a relationship is being established between the SNP information of those animals and their blood breeding values. And this is usually called the so-called key, and that key is basically then the relationship between the SNP information and the genetic merit of our reference population. Once you have the key, you can then genotype younger animals that you need to predict the breeding values for. Let's say a young bull that's a potential AI sire that you want to use. And so by having that genomic information and so-called, let's call it unlocking the genomic information of these young animals, you then get what we call a DGV, a direct genomic value. So each of these SNP effects are just summed up and or added together, and it gives you a direct genomic value. This is, however, then again combined with a blood breeding value, and that results in a genomically enhanced blood breeding value, or the GEBV. So it's two steps. It's the unlocking first, and then another blood run where once you've unlocked that, the direct genomic values are then basically begotten, and then another blood run is run where the GEBVs are then published as a genomic breeding value. So this is just illustrating it in a different way. And like I said, this is the initial way genomic information was combined with breeding value predictions. So where we only had pedigrees and records, or phenotypic records, we now add genomic data. There's also an estimate of the SNP effects, and that gives us a genomic breeding value. So you first need a fairly large reference population. You establish that relationship between the blood breeding values and the SNP effects, and that gives you a SNP key. So in these processes, the SNP key is being used to give you genomic breeding values without records, but that's again combined with the with the parent's breeding values, that gives you a combined genomic breeding value, or a GEBV. So it's basically two steps being used: the unlocking of the SNP effects plus the inclusion of that then in a blood breeding value as well. So the general model for a two-step would be, you would remember that the models for blood would have been your phenotypic value is a result of the group effect, or the animal's deviation from its contemporaries, plus the unknown breeding value, plus E. With a two-step, another important random effect is then added, and that is the summation of the SNP effects on all the loci. That's known in terms of the so-called SNPs in that. So that brings us to the latest technology that's being utilized, the so-called single step. And the biggest difference between a single step and a two-step is that the way that the genomic information is utilized in a single step is to change the A matrix. You will all remember that the A matrix is the average numerator relationship matrix. That's the additive relationships amongst the animals. So with SNPs information known of some animals in the population, the true genetic relationship amongst those animals can be established, not an average relationship. So in the case of, let's say, half sips, we know on average half sips are 25% related. But once the genomic information of those half sips are known, it can be established that some are more related than the average value of 25% that was assumed, and some are less related than the assumed 25%. So when the two genetic relationships are known, this is basically then utilized, and the A matrix is being changed. And then a blood run is just being concluded. So establish the real relationships first. You add that, and then the true relationships amongst these animals in terms of that is being utilized, and a blood run is being conducted. So the model itself is basically the same as with the previous blood models, except that your A matrix is being changed to a so-called G matrix, which is the true genetic relationships amongst the animals. This is just another way of expressing or illustrating that. You still have your population parameters, that's your heritability estimates and your genetic correlations among these traits. You still have your performance of your animals in terms of, or as a deviation from the contemporary groups or the fixed effects. But now you will have part of your A matrix will be the average enumeration relationship matrix as we have constructed it in our previous or previously, but we will also, for those animals with SNP information, where the genomic information is known, that is combined with your A matrix, and you end up with a genomically adjusted numerational relationship matrix. And that would then, you still have your two sources, outside sources, plus your population parameters, and that will then gives you a G blood or a GEBV that you can then utilize in your selection process. This has given rise to very interesting applications in terms of the true relationships amongst animals, the so-called principal component analysis, or where you can cluster animals according to their closeness or lack of closeness in terms of relationships, This is an example where some breeds were clustered together. Each of these dots represent an animal, and this is a three-dimensional plot, although we are only looking at the flat plane and 2 dimensions. So one would have been able to rotate this along an X, Y, and Z axis because it's three-dimensional, but you can clearly see how different breeds, these colors cluster together, since they are more related to each other than related to animals of a different breed. And this is currently being utilized globally by some breeder societies in terms of the quantification of so-called breed purity. Also, it also assists in making a decision whether certain lines will be included in so-called reference populations. It's also possible where you have breeds closer related to each other to join them in genomic breeding value predictions. It can also assist you if you have animals somewhere to assign them to a breed. And it also has a big advantage in terms of the importation of animals, as the genomic information can just be included in the blood run of, let's say, an AI bull that's considered to be imported, and those breeding values will be then expressed on the local scale, let's say the South African scale, if you want to import an animal like that. So from this section, we can maybe summarize to say what are the advantages of genomic selection. The biggest advantage is obviously that you will increase the rate of genetic gain, simply because your accuracy of genetic value prediction or breeding value prediction will be increased. So the ranking of your animals according to your breeding objectives will be more accurate, especially for younger animals, since you don't have to simply rely on a parent average anymore, as the genomic information will enhance your prediction accuracy, as the Mendelian sampling will be better predicted in this process. This basically is all, in most cases, because of a reduction in the generation interval, especially for traits that are sex limited or where you are unable to or record those traits at a young age, such as herd life, for example, where you have to wait very long before you know which animals will survive and which not in terms of your production system. So it also then reduces or eliminates the need for progeny testing, and that has a huge cost saving in the end, especially for artificial insemination companies that in the olden days need to keep bulls for many years before they knew whether what their true breeding values, or a higher prediction at least, on their breeding values were. So if we come back to the life cycle, just to illustrate the difference in terms of the age at which an animal will have an accurate breeding value prediction. This is the older life cycle. Remember, the bull, it took basically 5 years before the bull was progeny tested, and 10 years before his sons were progeny tested, and also many years before, for the same for a cow. So the generation interval is basically stretched out because of this. With the advent of genomic information, this changed completely. One can select young bulls, maybe still based on parent average, but then subject them to a genomic test, and by the first before they're a year old, by the time that you can tap semen from them, the accuracy of your prediction is remarkably high, and in the region, or in the same basically category as a bull with at least 10, 20, or even 30 progeny, depending on the heritability of the trait. So by just over 2 years of age of that original bull, you can already select his sons, his grandsons when he's 5 years old. And remember, you could only select the bull at that stage, so you're already 3 generations away compared to only 1 generation previously. The same for cows, possible dams of sires, you can already do the selection by the time that female is a year old. And with some of the accelerated reproduction techniques that's now available, like open pickup, you can even accelerate this process even further. So, a very interesting spin-off is also lower rates of inbreeding per generation, simply because you now know the exact relationship or genetic relationship amongst those animals. And one could think that because of the faster generation intervals, your rate of inbreeding could substantially be higher. But since you know the exact relationship amongst the animals, one can avoid those higher levels of inbreeding. This is just an illustration in terms of where you have the heritability on your x-axis and the expected inbreeding rates on the y-axis. You will see with classic blub, this is what is expected in terms of inbreeding rates. Just selection on phenotype alone, and with genomic selection, there's no difference in terms of the heritability because of the added accuracy in your prediction, and also the fact that the true genetic relationships are known amongst the animals. Some worldwide results, there might be newer results being published, but the North American dairy data shows a marked increase in accuracy of prediction using genomic selection, a jump from 52% for parent average to over 70%. In the Netherlands, also large increases in the accuracy of genomic selection over parent average, and also the same in New Zealand. So, like I said, there are numerous new examples of rapid changes in genetic gain at the onset of genomic selection. This is just a slide to show some other advantages of testing animals or with known genomic information. Obviously, the obvious reason for that would be genomic selection, but I've mentioned breed composition, mating advice. So many markers are being given on the SNP panels, so lethal mutations can be detected early. We have mentioned the prevention or the lowering of the rate of inbreeding, the prevention of some congenital deviations. Obviously, one can use this for traceability very well. It's maybe not a cheap process to do that. Karyotyping is possible, and very important that not just parentage confirmation through through genomic information, but also parentage discovery. Because of the high number of SNPs as markers, this is a very accurate way of dealing with parentage in livestock. That then brings us to the conclusion of this module of breeding value predictions, the TLR course of the University of Pretoria. Good luck, and please read through this thoroughly, and also the additional information that will be made available for you.